Hello. This video will talk about techniques of integration. We are starting chapter 7, and in chapter 7 we will develop a techniques of, for integration of more complicated function using the basic integration formulas. That means we will start with the first technique of integration, which is integration by parts. Before we start, let's look at the basic formulas, basic antiderivatives. Based on the fundamental theorem of calculus, we've got these formulas, we remember. That means the integration of the power function. That's one of the most important formula that we always using. Integral of x to the n dx is equal to x to the power of n plus 1 over n plus 1 plus the constant of integration. This formula works for any number of n except 1, and the negative 1 part is covered here. X to the negative 1, which is 1 over x, integral of 1 over x dx equals to ln of x plus the constant of integration. Integral of exponential functions are here. Okay? I also have the list of formulas of the trigonometric functions. That means they are just the direct antiderivatives. Integral of sine of x is negative cosine of x plus the constant c. Integral of cosine of x dx is sine of x, and so on. Okay, that means I don't have to read this. You can pause the video, you can copy this page, you can treat this as a reference page. I also have one more. Actually, we don't have to look at these formulas. Tangent, we can always use the u substitution, sine over cosine, and follow the u substitution and get the answer. Or if we're using a lot, an integral of tangent of x dx, you may remember that is equal to natural log of secant of x plus the constant of integration. And this is cotangent. And also in chapter 6, in the section of inverse trigonometric function, we also learn these formulas. Okay, that's me now. Let's start the list. Let's start the list of integrations techniques, and the first one will be integration by parts. That means what we have. Each integration techniques holds a corresponding differentiation technique. That means, for example, thinking about the u substitution for the integration, we always have inner function. That means we always have compound function. That means for the differentiation, the chain rule is involved. Okay? That means now integration by parts holds behind these techniques. It's the product rule for differentiation hidden. Okay? That means basically, based on the product rule, we can reverse this process and get the formula for the integration by parts. Okay, that means let's start actually with the product rule. Derivative with respect to x of the product of the function f times the function g. Okay, that means remember, f times g derivative, it's equal to f times g prime plus g f prime. Okay? And having this and using the fundamental theorem of calculus, I can integrate, right? I can integrate my right-hand side, and then I will get back my original function. Oh, too fast. Okay, that's we can see. I am integrating the right-hand side, and the answer must be the original function that was differentiated. Okay, differentiated. F times g. Okay, now integral of addition, it's simply addition of two integrals. Okay. And my last line, my last equation, I will solve just for the first integral. That means I will solve for this integral, subtracting the second integral from both sides. Okay, that means this is something that will help us to integrate a product of two functions. Okay? That's we can see, we will probably see something like that. F times another part, like I will call G prime at the moment. That means I will see one thing times another thing. And we remember we can't distribute, like integral of the product is not a product of two integrals, of course. That means having these two parts, f and g prime, we can rewrite like that. That means I can copy the same function f, and then g prime, looking at this as a g prime derivative, I can recover and I can get the function minus the integral of, again, the same g and f prime dx. And even if my original integral, it rewrites using the right-hand side, and we still see the integral on the right-hand side is supposed to be nice and easy. Okay? That means we definitely simplifying our integral. Let's use a little bit different notation. That means this is my part. And what I will do, I will nicely set up this. That means I will look at my original integral. Looking at the integrand, I will name one function u, which f of x is u, and the second part I will call g prime dx, g prime x dx. And I will call this dv, since I have to recover a function. That means v is g of x. Derivative of v is dv, derivative of g is g prime. Okay? And of course, I also need the derivative at some point of f. That means now let's see, f of x is u. Right? That means we can see I did replace f of x, and g of x dx is dv. And then my right-hand side will be rewrite as a u times v minus an integral of v du. That we really have to look at these settings, okay, and rewrite like that. One thing it's important, this part, f of x and g prime of x, these two functions will always come from the integral, the original integrand. Okay? And then since we need the other parts, we will differentiate f of x and we will integrate, we will recover a function g from the derivative, because we need g, we need v. Okay? That means these two underlying parts we always have to pull out from the integral and then work it out on the other parts and put to the formula. That means this is integration by parts formula. Okay, that means now let's start integrating. Let's start using this. I mean, this is quite important slide because it's showing me a theoretical part, the formula. Okay, we don't have to look at the solution for now. Okay, evaluate an integral of x times sine of x. Okay, that means what I see definitely two parts. I see x and sine of x. And since so far I only know one technique of integration for the product, which is the integration by parts, I will use the integration by parts. Okay, that means integration by parts. Okay, I need u. Let me use, oh, it's actually okay. U, and then du, v, and then dv. That means u and dv, these parts, I will pull out from my formula. That means I will let u be x, okay, and dv will be sine of x dx. As we can see, that's my integrand. And now I will need more parts. That means I have to differentiate u. Derivative of u du, derivative of x, 1 dx. Now I have to recover a function v having an integral. That means I will actually integrate, okay? Because actually having a derivative. That means what's the antiderivative for sine of x? I think it's negative cosine of x, because what's the derivative of negative cosine? Positive sine, okay? I do have my integration by parts, and now I need the formula. And we remember the formula was u times v u times v minus an integral of these two, v du. Okay, let's follow the formula and let's put u and v is negative x cosine of x minus an integral of 1 times negative cosine, which will be negative cosine of x dx. Negative x cosine of x, negative and negative is positive. An integral of cosine of x is just sine of x plus the constant of integration. And as we can see how the nice integration by parts formula did simplify everything, and we got an answer. Okay, example number 2. Evaluate just integral of ln of x dx. Okay, that means probably you will think, oh, I just mentioned that the integration by parts, we really need to see two parts. That means we have to see a product of two functions. And now I just see one function. But since we're assuming that we will use the integration by parts, let's make it a part. That means I will multiply ln of x times 1. That means one function is 1, the other function is ln of x. And let's use integration by parts. U du v dv. And now I have to let u to be ln of x, because if I will place ln of x here, ln of x dx, then I have to recover a function v, which means I have to integrate, and that's actually my original question. That means ln of x and 1 dx. And we can see again, please remember, u and dv. That's the parts that I see in my integrand. Okay, let's differentiate ln of x, 1 over x dx, and let's integrate 1, just x. Perfect. Now we need integration by parts formula. U times v, that means these two, minus an integral of the product of v du. Okay, let's see. U and v is x ln of x minus an integral of x times 1 over x. X, natural log of x. X times 1 over x, of course, is just 1. And integral of 1 is x plus the constant of integration. Again, we did end up with extra integral, that was relatively easy. Okay, blue formula, integration by parts. Example number 3. Evaluate t squared times e to the t dt. Okay, I do see a product. That means I will use integration by parts. Integration by parts, because that's the formula, that's the techniques for product of two functions. Okay, u du v dv. Okay, and since e to the t, derivative and integral is the same, that means I will place e to the t dt here. And t squared, the power function, I will let u to be this. Okay, and let's see. Of course, this, if you make the mistake, if you realize that something is not going in the right direction, you may always switch this. Okay, let's see. Derivative of t squared is 2t dt, and integral is e to the t, because e to the t derivative is e to the t. Okay, let's see what we can get. Formula is u times v, multiplication, I mean vu or uv, vu, uv, doesn't matter, minus an integral of these two, v du. Oh. Okay, and let's put our functions. V and u is t squared e to the t minus an integral of 2t e to the t. Okay, that's what I see. I still see, okay, I still see t times e to the t, which means I still see a product of two functions. That means I did simplify a little bit because originally I had t squared. Now I have just t. But I am afraid that, as always with any techniques, any tools, I have to apply the integration by parts also for the second integral. That means I will apply the second time. I will do one more thing. I will put 2 in front of the integral. That means I have t e to the t. And I will use integration by parts for this integral, the second time. Okay. Integration by parts. U du v dv. That means I will let u to be t and dv will be e to the t dt. Right, and let's see. Derivative of t is 1 dt. Integral of e to the t is e to the t. And let's see what we have. We have t squared. Shall I make a little bit wider? T squared e to the t. Yeah, I just copied this. Minus 2. And now we have to be careful because integration by parts for the second time. This is the second time. This was the first time. Okay, I'm just trying second time. Integration by parts, it holds the formula like in the expanded form. That's we can see we have two terms. That means that 2, this coefficient 2 will affect these two terms. That means, let's see, I can also put the formula u times v minus these two, an integral of v du. Okay, t squared e to the t minus 2, and let's see, u and v is t e to the t e to the t minus an integral e to the t times 1 e to the t dt. Okay, that means that's my formulas. And now let's distribute 2 t squared e to the t minus 2t e to the t. Negative 2 times negative will be positive, an integral of e to the t dt. We still have one integral, but it's just e to the t. Integral of e to the t is just e to the t plus the constant of integration. And you can check my solutions. Oh, I think this should be plus. Okay. Oh, my pen is gone. Okay, that means this is the example number 3, and it's showing me that I may apply the integration by parts twice. Okay, let's look at my example number 4. Evaluate an integral of ln of x over root x dx. Natural log of x over root x dx. Okay, that means I can't simplify, I can't really use the u substitution because that's also a technique that I learned. Okay, that means I am forced probably to use the integration by parts, and actually integration by parts works really well. The only thing is, okay, this is important example. You probably remember me saying 10 minutes ago that integration by parts, I mean, we can use the integration by parts only if we see a product of two functions. That means I can still use, but I have to rewrite my function as a product. That means I have ln of x times 1 over square root of x. Or I can use ln of x to the negative half. Okay, that we can see we do not have ln of x and root x. We don't have the function square root of x. We see as a second part 1 over square root of x. That means this is the common mistake too. You can apply the integration by parts, and we playing with ln of x and root x. We do not have root x. We have 1 over root x, or the power form x to the negative half. Okay, that means let's try integration by parts. U du v dv. And I have ln of x and x to the negative half. Of course, ln of x dx I have to place here. Wrong. Ln of x I have to place here because I easily know the derivative of ln of x. I don't know integral, which actually my example number 2 was, but that's not a point. Okay, and the power function I can put here. X to the negative half dx. That means one more time, I will let u to be ln of x, because derivative of ln of x is 1 over x dx. Integral of x to the negative half is x to the positive half over 1/2, which will be 2 x to the half. I can make, or I can actually write 2 root x. Okay, let's see my integration by parts formula. U times v, that is just the arrow. I have to multiply these two, u times v, minus an integral of the product of v du. Yeah, we can see product of these two. Now, if you will set up this box, okay, this table, you will never make the mistake. That means you don't even have to memorize the formula. You will just remember the horizontal line and the diagonal. Okay. uv, 2 root x ln of x minus an integral of 2 times square root of x times 1 over x dx. Okay, we still have an integral, but I believe it's not a problem because square root of x is x to the 1/2. 1 over x is x to the negative 1. We can combine. That means we do have x to the power of 1/2 minus 1. Too many times. That means this is an integral of x to the negative half dx, which actually it's funny, we just did this exercise. Okay, let's put the final answer. 2 root x ln of x minus 2, an integral of x to the negative half is 2 root x. 2 times 2 is 4, but I don't have room to rewrite. Okay, yeah, that's when we can see what we did. This one is important. I can probably highlight this part. Yeah. Please do not use the square root of x. 1 over square root of x. Okay, let's see my example number 5. Evaluate an integral of e to the x times sine of x dx. Okay, yes, again, it's a product. I will use integration by parts. Integration by parts. U du v dv. And both of the functions are relatively easy for integration and differentiation. That means I will possibly put I will let u to be sine of x and dv e to the x dx. Derivative of sine, it's cosine of x dx. Integral of e to the x is e to the x. My integration by parts is a product of these two and minus an integral of the product. uv minus integral v du. Okay, e to the x sine of x minus an integral e to the x times cosine of x. Oh, well, I kind of simplify, but to be honest, this integral looks almost the same like this one. Okay, but let's see what's happened. Of course, we learned 2 slides ago that we may apply the integration by parts for the second time. That's mean by parts, and I will focus on this. U, du, v, dv. Okay. And since the first time I let u to be sine of x, the second time I will also pick a trigonometric function. U will be cosine of x, and dv e to the x dx. Derivative of cosine of x is negative sine of x dx, integral of e to the x, e to the x. That's mean my integration by parts is u times v minus an integral of the product of v du. Okay, let me put e to the x sine of x minus, and I can put the formula for you, uv minus integral of v du. And let's use the green box. E to the x sine of x minus, and we still have to remember negative in front. This negative will affect both numbers. Okay, uv is e to the x cosine of x, e to the x cosine of x minus an integral e to the x times negative sine of x dx, and I still have to close my green bracket. Okay, let's see what we have. E to the x sine of x, distribute negative, negative e to the x cosine of x, and now let's be really careful. Negative, negative, and negative. That means I do have 3 negatives. Oh, 3 negatives is actually negative, because negative and negative is positive, and another negative is negative. Integral sine of x dx. Oh, well, okay, I did lots of work. I did apply the integration by parts twice, and what I'm getting? I'm getting the same integral, the original integral. That means probably I have to stop applying this integration by parts, because applying for the third time, I will end up with e to the x cosine of x. Applying for the 4th time, I will end up with e to the x sine of x. Okay, that's what we have to do. I will do something, let's see, that means I know that this, whatever I've got, it's my original integral, e to the x sine of x dx. Okay? And I just copy this integral. That means I will take this as an equation, okay, and I will name my integral I. And since I see on the other side, okay, the same integral, I can simply solve this equation for this integral I. That means this is I, okay, it's equal to e to the x sine of x minus e to the x cosine of x minus I. And let's solve this equation for I. Okay, I will add I to both sides, which means I do have 2I. I don't have to write this for you. We are a little bit more advanced. And e to the x sine of x minus e to the x cosine of x, and I will divide by 2. That means I is e to the x, and actually I can factor out sine of x minus cosine of x all over 2, and plus the constant of integration. That means this is I, this is my integral of sine of x dx. And this is the final answer. What color I can use maybe the same. Okay, that we can see we kind of like create an equation with the unknown being our integral I solve the equation for I. That means I equals to e to the x times sine x minus cosine x over 2 plus the constant of integration. That means this is interesting type. It's a little bit, yes, a little bit different. Okay, that means I think I had only 5 examples for this session. I have one more slide with kind of like a summary. Because what I did, I was choosing u and dv. U and dv. Yes, like function f and g prime. And what I do have a special, I list a special types of the function that are good for integration by parts. And now I have a little bit of tool of choosing the first value, u, the first function, u. That means let's look at the types. Typical types, x to the n times e to the power of ax. That means power function, or I can call algebraic function, times exponential. Exponential function times trigonometric function. Algebraic function times logarithmic function, and just the inverse trigonometric. Because then we can multiply by 1, or just the inverse, because even ln of x was an inverse of e to the x, and we multiply by 1. Okay, that means having all of these types, let's see what we see. Whichever, let's see the tool for choosing u. Whichever function comes first on that list should be chosen for you. Okay, that means if you see these types, look for the inverse trigonometric function. That means if you see the inverse trigonometric, this must be you, chosen for you. Then if you don't see, look for the logarithmic function. Logarithmic. Like you remember, I choose the logarithmic. I let u to be ln of x twice. Actually. Then the next one in the line is algebraic function. Algebraic is this, x to the power of n. Then trigonometric function, and the last one will be the exponential. Okay, which you probably remember, I didn't put exponential function for u. I just put for dv. And the first letters I, L, A, T, E kind of like create the words I latte, I late, E latte, whatever we can pronounce. That means it's worth to remember I late, I latte, and of course we have to know what these letters stand for, and then that's the tool of choosing the function u, the part u, because the function lower on the list have easier antiderivatives than the function above them. It's easier to differentiate the top function rather than integrate. Okay, that means you can think, and we will still solve an integrals by parts, but this is the nice summary. Thank you.